Hello and welcome to another video. In this video we're going to be working on paths with maximum probability. And in this one you're given an undirected weighted graph of n nodes represented by an edge list where edges is an undirected edge connecting between A and B with a probability of success of traversing that edge success. Given two nodes start end, find the path with maximum probability of success from start to end and return it. If there's no path, return 0 and it will be accepted if it's close enough. So in this example, the start is 0 and the end is 2. So there's kind of like two ways we can go there, right? We can go here, and the probability is 0.2, or we can go here. I mean, there's other ways we can go, but they wouldn't make any sense, right? You never want to like go somewhere and then go back, because if you go somewhere and go back, it's better to just not go anywhere at all, right? Like here and back, the probability is 0.5 squared, and not moving is just 0. So the two ones that make sense are this one and this one, and 0.5 squared is 0.25. Oh, is that right? Yeah, I think so. So 0.25 is better, so this is the best path. So hopefully that makes sense. Like you just figure out like there's a bunch of paths. What paths, if you multiply every single edge, essentially, what gives you the least? Or the most, sorry. And then here, so we have the start is 0, the end is 2. So we can go this way, which is 0.3, or we can go that other way, which is 0.25. So 0.3 is better. And then here we have 0 and 2, and they're not connected, so you just return 0. And so this is another important thing. Look at constraints, because that'll help you figure out like what to do. So I'll talk about some of these. So first of all, here is kind of important. So 10 to the 4th, so n squared will fail. Start and not equal to end, also good to know, because then you don't have to worry about like, am I already at the start or something? You don't have to check for any of those. A is not B. So, I guess it's just saying a node won't be connected to itself, which doesn't really matter because if a node's connected to itself, you never really have to like go there anyway. But I guess that would be something to check for, right? You'd never want to like do that, but even if a node was connected to itself, it would still be fine for this. And then edge's length, the success probability, and this is another important one. And so this varies between problems. There's at most one edge between two nodes. So here, sometimes you'll get problems that you have multiple edges between two nodes. And then depending on the problem, usually you can just eliminate them. So for example, here, we're trying to get the max probability. So let's say this edge is 0.3, and then we have another edge that's like 0.6. So generally for these problems, you're going to make a graph, and then you just figure out, like, do I want to keep the biggest or the smallest edge if I have duplicates? And in this case, you would want to keep the biggest. But you don't have to worry about it because there are no duplicates. But if there were, you would just say like, okay, let me just store the biggest. So if I've seen an edge between these two nodes before, let me just store the biggest one. In this case, they kind of have simplified it for you. And so the way to do this is basically using Drixer's algorithm. And so you should be familiar with like how it works. I'll briefly describe it, I guess. So let's see if I have a graph thing here. I guess I don't, but I can show a graph like a tree. So imagine this is a graph. So these circles are nodes, and then the lines are edges. So you can have a graph like this, right? Like this is a valid graph if these were all nodes and these were all edges. So basically what Drixter does is you start at some node, and you go to some other node, and you keep track of all the paths you're currently on and their total distance. And then you just simply keep taking the smallest one. So what that would look like is, like, let's say you start here. So there's only one path, so that's this path. But then from here, you would have two paths, right? So there's one path here and another path here. And then if there were more paths, you would keep track of those. So from here, there are two paths. So here's like a dead end, but here there's two paths, right? So path 1 goes over here and path 2 keeps over here. And so essentially you would have these two nodes stored, and you'd see like, okay, which one of these is shorter? And then the one that's shorter, that's the one I'll try first. So essentially you're keeping all of your like active paths in a heap, and then you keep returning the smallest one. And if you keep doing that, like let's say this whole path is like length 10 and this whole path is length 12, then you would say like, okay, let me explore from here first, whatever this is, and then let me go find some else. So for example, if this was only length 1 and this whole path was length 11, right, from here to here, then you would explore this node before this node. And so that's kind of the idea. You just keep like a bunch of nodes stored in a heap and the distance it took to get to them, and then you always pop off the smallest ones because that'll give you the best. And if you've already visited a node, like let's say obviously here there are no like there are no ways to visit the same node twice. But let's say we take this and say like we can visit this node in a couple of different ways. Maybe we can get here from here, or maybe we can get here from like here or something. Then basically the idea is like whichever node you get here first from, like let's say this is, if this was distance not probability, let's say this is 1, this is like 2, this is like 3, 4, 5, whatever. These are just distances 10. So you can get here with a distance of 3, right, going this way. And you're guaranteed in Jigstras, whenever you visit a node, you will have visited in the shortest distance possible. So if you try to visit it again, then you like ignore that. So you usually keep like a visited set of nodes you visited and so on. So that's the basic idea. I'm not going to go like into huge detail because I don't want this to take too long. But so if you know that, so Jigstras can give you shortest distance, longest distance. You basically just change a few variables, right? If you want shortest distance, you would just keep popping off nodes with the shortest total distance. If you want the longest, you would pop with the longest total distance. But how can we relate this to probability? So probability is pretty similar to distance. If we want max probability, like if we have a bunch of numbers, how do you maximize probability? Well, you just keep taking the bigger number, right? Like if I have a probability of one thing going like 0.8 and I have another one that's like 0.2, I'd want to try the 0.8 because that would maximize probability, because your total probability is just the probability of A happening, then B, then C, then D, and so on. So imagine if this distance didn't ask you for like what's the total distance like added, but what's the total multiplied distance. You'd still kind of do the same thing, right? If it was like asked, like if it said the distance from 0 to 2 is like all the things you go on multiplied by each other. If you want to minimize it, you would just pick the minimum distances. And if you want to maximize it, you'd pick the maximum. It's the same with probabilities. So if we have a choice, let's say from here to go here and here, we're going to traverse the one with highest probability first. So what it's going to look like is we start here, then we're going to come over here. And then basically we have two options. We can either go here, and we're going to have the probability stored to get here, right? So the probability to get here is 0.5. So now we have an option of like, we can either go from here to here or from here to here. So if we go from here to here, the total probability will be, actually, no, it's not going to work like that. It's going to work like this. So we start here. So actually what's going to happen is we're going to take all of the nodes we can visit from the starting node. So actually we will visit both of these. Yeah, well, we won't visit them, but we'll put them in our heap as like, this is a possible path. So we'll have both of these as a possible path. So this is 0.5 and this is 0.2. Then, because this is bigger, we're going to pop this from our heap. And then we're going to push this onto our heap as well with this total distance. So what's going to happen is our heap will have 2 with a value of 0.2, and then also 2 with a value of 0.25. And because 0.25 is better, that's the one we'll pop off, and that's the one we'll return. So essentially once we visit a node, we put all of its children that we haven't visited on our heap, and then we pop from the heap the one with the biggest probability, and then those are the ones we visit first. So that's kind of the idea. So here, same kind of thing. You would put both of the children on the heap. So this has a probability of 0.5. This has a probability of 0.3. You would pop this off because it's biggest. Then you would put this child on again because we haven't visited it yet. So we'll have this with a probability of 0.3, and we'll also have it with a probability of 0.25, and we'll pop off the 0.3 first, and then we'll get our answer. Yeah. And then this example, what's going to happen is we're going to put all the children on their heap. So it's going to be just this with a probability of 0.5. And then from here, we can't go anywhere because we've already visited 0. So we pop this off, and then we can't get, like we are going to have an empty heap, and we can never get here. So we just return 0. So that's kind of the idea. We just keep popping off the heap until we get where we want to go. Or if we never get there, we just return 0. Okay, so yeah, like I said, this is kind of important because you can figure out if you need to simplify things. And yeah, let's say you did have like 100 nodes and a million edges. There's problems like that. It's very simple to figure out which edges you need. So you wouldn't store like every edge. Like if this has like 50 edges, you'd just store the biggest one, because you're never going to want to traverse an edge that's less probability if you can go the same way. And if you're trying to do like smallest distance, then you would just store like the smallest edge and so on. So it depends on the problem. All right, so I think I covered everything we need to here, and now we can code it. Yeah. Okay, so you can do this a few ways. So basically what you need to in a heap, I guess I didn't cover that, is you want your heap to be, to be sorted by something. And so in this case, our heap needs to be sorted by probability. Right? So we need to store the probability and the node that we're on. And because so you could do this in a few ways in Java. You can either store them both as a double, right? Like if it's 1, you can just store like 1.0. Or sometimes you'll have like different data types, and in something like Python, you can store like a double and an int or something. But what I found is kind of useful, especially over your heap, is we can just create a new type, and we can call it like a tuple, and then that way you can have like whatever types you want. So we can just say like class tuple. And then we'll have a probability field and a node field. And then we can make a constructor. And you can use this for just generic tuple, so it's kind of useful. You can have like as many types as you want in here. And so we want the probability, and we want the node to be the node. And then what we can do is, because our heap needs a comparator, we can make a comparator function, and we can just pass it into our heap. And we can make this static because we don't need to make a tuple to have a comparator function. So this should be shared throughout all tuples. So we can say tuple comparator. I have to look this one up. Implements comparator. And you have to give it the type, so in this case tuple. And then we basically just want to override the default. So we say override. And because a comparator returns an integer, I think it returns like negative if things should be in front, or positive if they should be behind or something. So we can have public int compare function. And this function is going to take two tuples, so tuple 1 and tuple 2. And now we can just return a comparator. So typically you want to return a negative number if tuple 1 should be, I think it's like -1, but I think you just need a negative number if tuple 1 should be first, 0 if they're equal, and a positive number if tuple 2 should be first. So in our case, we actually want the bigger number first, right? We want the bigger probability first, so it's pretty easy. So we can have a double comparator here, so we can say double compare. So typically, if you do like double compare AB, that will make things sorted in increasing order. So like if you did this way, T1, T2, that would make it sorted in increasing order. So all we have to do is just swap it around. So we'll say T2 first. Or you could use a negative value as well, would work, I guess. So we're basically saying for our tuples, we want to compare them by probability, and we want it in reverse order, so we'll do T2 first. Okay, and then now we can actually do the rest of it, and we can use this tuple for everything else. So we can say we want a priority queue heap, but we want it of type tuple. So heap equals new priority queue. And then we can pass our comparator function that we made down here. So that's why it's kind of convenient. You can do whatever you want here. Tuple comparator. And then we're going to make a visited. So you can use a visited set. I'll just make a visited array because we know it has n values. So we'll just say Boolean array visited equals new Boolean array. And we know it's of size n. And then we want to fill it with false. Okay, and now we want to make our graph, so we can say map integer, and then all the nodes in here. So this is, like I said, this is where it matters if you have duplicate edges. Because we don't have duplicate edges, we can just make a list of children. If you had duplicate edges, you'd probably have to have like a map of maps or something like that. So here we can just use a list of tuples. This is just a new hash map. Okay, and then we just have to loop through all our edges. So less than edges length. Okay, and then we have to say our edge is edges I. So because the edge is at index I, and the probability of that edge happening is at success probability, so that's what we have to use integer here. And so we can just say like x equals edge 0, y equals edge 1. And so this is another convenient function you can use. So if you have a map that has like an integer or whatever, string as a key, and then some kind of list or something as a value, what you can do is you can do this. So you could say graph compute if absent, and then you pass it your value that you want. So in this case, for a key X, if this list of tuples doesn't exist, we can just give it a function to make it. So you just give it anything here. This is not going to be used at all. And then we just say, like, let's just make a new array list. So if it's not there, if this key is not there, put in the key and put in this array list for the value. And then we can just add on to here. So then we could say, like, if it is here, then it'll give you the value. And then we can add on to that. So we're basically saying, like, if we have a graph and we're putting on like the value 5, let's say a graph is empty, for 5 it will make a new array list and then access that array list, and we can do stuff here. And if it already has that array list, it will just access that array list. So compute if absent will either make it and return it, or just return what's there already. And then basically we want to add a new edge here. So this will be, we just add a new tuple of success probability I and the node we're going to. So X is going to Y, and then Y is going to X, because this is a unweighted graph, so you have to add an edge in both directions. So this way and that way. Okay, now all we have to do is add our starting, we're going to add our starting node to the heap. So heap add new tuple, and the probability. So that's the other thing I don't think I talked about, is wherever we start, the probability is 1, right? Like if we start here, the probability we start at is 1, because we're already there. So our initial probability is 1. So that's another important thing to figure out for this problem. And then this is just start node. And we want to just say while our heap is not empty, so is empty, keep popping. So cur pop from the heap. And we want to check, is this the actual node we're trying to get to? So if the current node, what did I call it here? Oh, current dot node is the end node, then we're basically done. So we just want to return the probability that we arrived to this node at. If it's already visited, we want to skip it because we've already visited it with a shorter path. So continue. Otherwise, we want to add it to visited. So visited cur node is true. And then we basically want to check if it's in the graph and it has children, let's add all the children that we haven't visited yet to our heap. So if graph contains key cur node, then we want to get all the children. So remember, this is a map of tuples, list of tuples. So tuple child, graph get cur node. So we basically just have to check if it's not visited. So if not visited, child node, because every tuple has the node and the probability. So if it's not visited, then add it to the heap. And here we have to add a new tuple because this tuple child is just the probability of going from the parent to the child. But we got to the parent with usually a non-zero probability, right? Like if we go back to this tree example, or even something like this. Let's say we start at the top, or let's say we start here, and we got to here. So if we got to here, let's say, we didn't get here with a 1 probability usually, right? Because we have to like multiply all these probabilities. So when we go to this node's children, this node's child's probability might be like 0.5, but we might get to this node with like a 0.1 probability or whatever. So the actual probability we get to this node is the probability we get to this node times the probability of the child. So that's why we have to make a new tuple. And this is going to be the child probability times the current probability. So it's the probability we got to the current node with times the child, and then the node is the child node. Okay, and then basically the only thing left is if our heap is empty and we didn't find the node we're looking for, we just return 0 because there's no way of getting there. And hopefully we didn't do anything wrong. Let's find out. Maybe not. Okay, good. Okay, so like I said, you can code this in a bunch of different ways. I think in Java, the most efficient thing is using arrays like everywhere. So you can probably, instead of the map, you can use like a nested array or something, like a 2D array. Ideally, instead of this tuple heap, you can probably use a double array and so on and so on. And then that would give you like the best runtime probably. Like if we look here, this is probably what happens. Yeah, so probabilities is an array. Yeah, just use an array for like everything. It's going to be the best. I don't think this even uses a heap, so Interesting. Okay, but yeah, anyway, so for Dijkstra's, mainly you have to know like the runtime here. So let's figure it out. Before we actually figure it out, I'm curious what it says. And log in. Okay, so let's try to figure it out, see if that's correct. Okay, so we have n nodes and we have e edges. So if there's at most one edge between two nodes, like if there are no duplicate edges, you can basically have, so if v is the number of nodes and e is the number of edges, e is going to be v squared, like worst case, right? Like imagine every node has a edge to every other node, that's roughly v squared. Okay, so anyway, so let's see. So we make a heap, that's nothing. We make a visited array, so that's n, so we can call this like v. Usually for these, I just use v for vertex and e for edge. And then we fill it with false, which is n. And then for every edge, we do something, so that's e. Okay, and then we add to the heap. And so while the heap is not empty, we add tuples, and then basically so I kind of showed you earlier that you can have the same node. You can have the same node in the heap multiple times, right? Like in this case, right? Like we can have 2 on the heap multiple times because we'll have it from here and we'll also have it from here. So you can actually have a node multiple times, but I think they usually don't account for that. So I think it's usually something like, well, I guess you can't have more than like edges. Yeah, you can't have more than edges. So I guess you could say like, it's probably going to be something like, for every vertex, we can only pop off a vertex once, so, roughly. So usually you can write like something like this, or probably like this actually, because edges are separate, something like this. Or you could say that this can technically be this as well, but then the thing is, I think for logs the power falls off. So I think it's something like this. Not exactly sure. I like never get these right. And then for space, so the graph can contain every edge and every node, and then the heap can contain basically. So I think worst case scenario, it's like e. Because e can technically be worse, like e can technically be v squared. So, but usually I think people write this. I think this is like the accepted one. I'm curious what, I guess we can check here. So there's probably a Dijkstra's one. Okay, that's Bellman Ford. Let's see, shortest path, faster or something. N plus M. Okay, so this one's a little bit better, it looks like. Q. Yeah, so here we go. So Dijkstra's is the one we used. And I think they usually, yeah, so n plus m. I guess we did have n plus m, right? So, yeah, so n plus m, and then time is n times m, and we had, yeah, so that's the other thing is like, even if it was n times m, so if you have n times m, or n times m log n, like the log adds so little that it basically doesn't matter. So I would say that's basically the same thing. And this is like a generic thing. I think I've done some Bellman-Ford problems. I think you only need Bellman-Ford when you have negative edges, but we don't have negative edges here. So you could learn it if you want to, but I basically use Dijkstra's for like 90% of graph problems. Yeah, I think we're going to end it here, and hopefully this was helpful. If it was, please like the video and subscribe to the channel, and I will see you in the next one. Thanks for watching.